Hello everyone. So welcome to the second lecture of our RCC building design using ETABS and manual checks course. So in this lesson, we will be seeing the evolution of structural systems. Let me write it properly here. The evolution of structural systems, and we will be talking about more in terms of concrete structures, as we will be dealing with RCC structure in our throughout the course. Okay, so let's begin with the very basic one that we see every day. If I just draw a structural plan here of a building, so this kind of structure you may see everywhere every day. Suppose I'm just drawing roughly. Suppose this kind of grids you may have. So I have drawn the beam plan, and if I place the columns, suppose at the column positions, that at the positions. At every beam junction, columns. Okay, and suppose in this area we have a lift shaft where the lift will be coming. I'm just drawing roughly, and maybe here we have the staircase here, something like. So this is a corridor. This kind of structures we generally see everywhere. This is a corridor here, corridor, and these are the rooms. Here we have staircase, here we have stair, and here we have lift. Now this kind of structures where we see in school buildings, in office buildings, there will be a single corridor, and both sides will be having rooms like this. You may have this lobby, and this is the corridor. You have rooms everywhere. Now if I just draw a let me draw a axis for this particular structural system. Suppose if I just draw a axis here, suppose this is x, and the which is going upwards, it is y axis. Okay, so now if you just see here how many frames it will be, like it will be something around like this. If I see, suppose from this direction, so it will be like this. The 4 columns will be there. Suppose it is g plus t, so g 1 2 3. Okay, so this will be something around something like this, the elevation of the structure from this direction. And from this direction, if you see how many columns, 1 2 3 4 5 6 columns. Right, and okay, g plus 3, so g, just make it a bit bigger, and we have 1 2 and okay, I'll just, these are the fixed joints I'm considering. Now if I just write you can say along x direction, if you see how many frames we have, water frames, I will just explain in a while water frames. So just remember, frames are the vertical and horizontal members connected with rigid joint. So all these things I will be explaining in depth in this lesson. So if you see here, along x direction, how many frames we are having? We are having 1 frame, 2 frame, like here. If you see this particular one along x direction, this particular one is a frame. Particular one is a frame as a whole. So if you see this direction, 1, 2, 3, 4, 5 and 6 frames we have in this direction, right? Along x direction, right? And along y direction, how many frames we have? 1, 2, 3 and 4 frames we have. So 1, 2, 3 and 4 frames we have, right? Again, sorry, what I have done, I think I'm saying wrong. If you see along y direction we have 6 frames. Okay, along y direction, I'm just doing it in the wrong way. So along y direction we have 6 frames. Frame is 6. Along x direction, okay, this way we are going like this. So how many frames we have? 1, 2, 3, 4. So along x direction we have 4 frames. Now what these frames will do? When we will be having dead load and live load, the gravity loads, as I've explained in our last class, these all the columns will be able, all the frames will be able to take the gravity loads. That's not an issue. But when we will be having the lateral loads or the horizontal loads in terms of seismic force or wind force, in that case these frames, if you are seeing here, these frames along x direction, okay, these are the frames which will be resisting the force which is coming from x direction. These frames 1, 2, 3, 4. This is one frame, and similarly we have 4 frames here along this x direction. Okay, it will be resisting the force which is coming from x direction. And similarly these frames 1, 2, 3, 4, 5 and 6, which are along y direction, will be resisting the force coming from y direction. Okay, so I will just write it fx and f. Now if you just see properly that, okay, we have got how many number of frames? 6 number of frames along y direction and 4 number of frames along x direction. But if I just consider the number of bays, in that case, if you see along x direction, along this direction, we have 1, 2, 3, 4, 5 bays. So number of bays along x direction, we have 5 bay, right? This 1, 2, 3, 4, 5 bay, okay, along x direction, right? And if I see along y direction, how many bays we have? Along y direction we are having 1, 2, 3 bays only. So 6 frames in y direction but 3 bays only. 4 frames in x direction but 5 bays we have. So it is pretty simple to understand, as we are having higher number of bays in the direction of x. So it is if you see the dimension of the in the direction along x direction, it is pretty simple that the stiffness or the strength of the structure or along this x direction to resist the lateral force which is coming from x direction will be higher, right? And compared to if fx and fy are equal, then in that case the force which is coming from fy direction, the frames that are having along this direction, this y direction, as it is having only 3 bays, it will be weaker, right? It will be weaker. So in this particular building, the y direction is weaker in terms of resisting the lateral force. The x direction is stronger in terms of resisting the same amount of lateral. But still, when the structure's height is pretty low, like g+3, g+4, in that case, this kind of structural system with the column and a beam, though it is weaker in this particular direction, but it may able to you can say resist the lateral force which is coming on this particular structure. Okay, now if I increase the height of this particular building, suppose I have increased it to g plus 8, something like this. Okay, so similar structural bay I will just draw here. Just make it a bit longer. Okay, here fine, and I will draw the columns also. I will not draw the lift and all. You just imagine that there is a lift core, not core, lift shaft here actually. Core is a different thing, I will explain. So suppose previously we are having this kind of structural system, right? Now if as the height increases, let us make it g plus 9 or g plus 9, 10-story building, or g plus 10 or g plus 11 or whatever, 12-story building. In that case, maybe the force which is coming from x direction, as the number of bays we have 1 2 1 3 4 5, as the number of bays are more here along this direction, maybe these frames will be able to you can say resist this fx force. But in the y direction, the fy force may not be resisted by the structural system, or you can say by the frames present in this direction, right? Like these are the frames 1 2 3 4, these frames we are having, but the number of bays we have 1 2 3 only here, so it may not be able to resist the structural system, resist the lateral force. So in that case, what we need to introduce, one more structural element that I have discussed in our previous lesson, which is called the shear wall. Is called the shear wall. So suppose no, I will not draw here. Let me just remove this. And draw properly. Okay. So now here what we need to do, we need to introduce shear walls. So suppose I am giving shear walls here and here. Okay, I have given shear walls here and here. Now what are these shear walls? What are shear walls? Shear wall, what is the shear wall actually? Let me just write it here. These are the shear walls. Now before explaining the shear wall, let me just explain, as I have said that these are the frames and base we have, and this is the shear wall. So let me just give a bit explanation about the frames. Okay, let me just give a bit explanation about the frames. So if I just write the type of frame and the definition of frame, I will just write the definition of frame letter. Let me just write the type of frames. Type of frame. Now we have two type of frames. One is braced. I'm just giving very simple you can say classification, and we have rigid frames. We have braced frames and we have rigid frames. Okay, now in braced frames, if I just write the characteristics of a braced frame, so what you will find that the braced frames, if you see the joints of a braced frame, then these joints are hinged. the joints are hinged. Okay, joints are hinged. In brace frames, you will find bracings. Bracings you will find in brace frames. Obviously, that's why it is named as a brace frame, and it is very essential structural system in terms of the brace frame. And this kind of brace frame with bracings we normally give in steel structures. We normally give in steel structures. Okay, so and in the rigid type of frame, here the joint between the members are rigid. So rigid joints we see between the members. There will be no bracing. So as the joints are rigid, it is there will be no bracing, and this kind of you can say frame, rigid frame, we see mostly in RCC structure. Mostly in RCC structure. Now, what is actually a frame? Before knowing that, what we need to do, let us know about, okay, braced frame. If you see, it is just the members, as I said, members connected with you can say hinge connection, right? Hinged joint. So suppose there are different types of, you can say, braced frames. So suppose these are two vertical elements, these are the horizontal elements, and as I said, there will be bracing. So suppose here I am giving the bracings like this. I can draw another type of braced frame, vertical members, horizontal members, and we are giving bracings like this. You may see this kind of structures, steel structures, industrial structures like this. We can draw another type of braced frame. I will just name all of this. I'll tell you the names also. Suppose we have this kind of bracing in the structure. So do we see this kind of bracing members in concrete structure? No, right? In most of the cases, we see this kind of bracings in steel structures. So again, there can be a type like this, right? There can be a type. There are numerous types, but I'm just giving you the few very popular one. So you may have this kind of bracing, and you may have, close it, you may have this kind of bracing. This kind of bracing also, right? Another type, let me just draw here. You may have this type of bracing. Okay, it is not connected to each other. It is a bit at a distance. It is not like the same as this one and this one are not same. Okay, will be okay. Now, what are this type of brace frames called? If I just name it number 1. So what we have done, we have given diagonal bracing here. Here we have given X type of bracing. So these are the X bracing or cross bracing, you can say. Here we have given inverted V type of bracing. So it is inverted V. Write it here. Inverted V. Here this one, obviously it is V bracing. This one you can see it is a K bracing. This one we can write it, this is the this is named as knee bracing, and these are called eccentric bracing. Eccentric bracing. Okay, this is diagonal and this is cross bracing or X bracing. Okay, now this type of structural system we see mostly in our steel structures, industrial structures, warehouses, right? So if you see this first, second, third, and you can say this one fourth, this four, if we have this type of bracing, and obviously these bracings we used to provide at the outer periphery of the structure. Okay, because if these bracings are provided at the inner periphery of the inner side of the structure, then it will be very hard to move around, because these bracings will become obstruction for us, right? So these bracings are provided at the outer periphery of the steel structure. Now the problem with these bracings are it is very hard to provide doors and windows with this kind of bracing. So we need to give the bracing in like that, so that we can accommodate the doors and windows also. So if you see though it is possible in case of this V type of bracings, but it is very hard in case of diagonal and X bracing. Okay, and it is very easy. It seems very easy in case of eccentric bracing, in case of K bracing. Okay, in K bracing also you may find some difficulty to provide the doors, but knee and eccentric bracings are you can say functionally it is very you can say effective, because we can provide the doors and windows, but structurally these are weak. Structurally, if you see the knee and eccentric bracing, these are structurally weak. Functionally these are good. This diagonal X bracing, these are structurally good, but functionally they have issue. Okay, but so these are my you can say braced frames. These frames which are connected with hinged joint and having bracings in the with them are called the braced frames. Okay, now which frames are called as rigid frames? So first we need to understand what a rigid joint is actually. Okay, we need to understand what a rigid joint is. We have already said like you can say here you can see what we have explained. So we have explained here the frames, the shear wall also. Okay, so we I think I should have explained the frames first. Let me fix this. Okay, no problem. So we need to understand what rigid frames are. Now let us understand what rigid frames are. So first I will write about the rigid joint. So rigid joint is a kind of joint. Suppose we have two members connected here, and we have got this joint, this particular, right? Now whatever force is coming on these two members, okay, this joint should be capable of transmitting the full extent of the force. Okay, whatever force, suppose A force is coming here, B force is coming, these forces, this particular node should be able to transmit full extent of these forces to the connected members. Okay, if it can do so, then these joints are called rigid joint. Full extent of the force. Here we are giving hinged joints, right? The pin joint. So obviously the moments will be released, or like in steel structures you say moment connection, shear connection. So the connections, we do not call those as fixed connection or like rigid connection, right? So here this particular node is capable, should be capable, maybe not 100%, but in a very major extent it should be capable of transmitting the forces coming to these connected members to other member. Suppose this force should be transmitted to the vertical member through this joint. If it can do so, then this particular joint is called as rigid frame. Okay, now sorry, rigid joint. Now the frames or the members which are connected with the rigid joint and create this kind of bay are called rigid frames. So if I just create like this a frame, and these joints, we are considering that these joints are capable of transmitting the forces, the full extent of the forces to each other from here to here. Then through this joint, then this frame will be called as rigid frame. This frame will be called as rigid frame. So here is rigid joint, and the frames having rigid joint named as rigid frame. So where we see this kind of frame, if I just draw a 3D frame like this. So mostly in case of concrete structures, you will see there will be no bracings and all. There will be only beams and columns like this, and these beams and columns are having this kind of joints which are called rigid joint. Okay, so that's why most of the concrete structures, if you see, the frames available in the concrete structure are actually rigid frame. Okay, and joints are rigid joint. So now if I go back to my previous explanation where I was explaining the shear wall. So previously, here you can see we have the frames connected with the rigid joints, and it was taking the forces, lateral forces, resisting the lateral force. Now here, as the y-axis is weaker, to take or to resist the lateral force, here the x-axis is pretty good. Okay, these columns are capable, or these frames 1, 2, 3, 4, the whole frame. Okay, this is a frame from here to here. This is a frame. This is a frame. Okay, this whole 4 frames are capable of taking the force coming from the x direction. But in the y direction, these frames, the 6 frames we have, these are not capable of resisting the Fy force. So that's why what we have done, we have given a shear wall, 4 shear wall here. Here you remember we had lift shaft here, and we have shear here, right? And in these 2 sides we have given shear walls. Now what are shear walls? Shear walls actually structural walls. Shear walls actually structural walls. This can be made up of concrete if it is a steel structure, steel plates. Okay, deck plates are also steel plates are also provided to create the system like structural wall or shear wall. But in concrete structures, we see that these are the concrete walls, RCC walls. I will say properly, these are the RCC walls, and these RCC walls are meant to take the lateral force. Obviously, these RCC walls can take the gravity loads also, but these are actually meant to take the lateral force mostly. Okay, so if the structural wall is constructed, or the structural wall is provided in a building to take the lateral force or to resist the lateral force, then those structural walls are called as shear walls. Okay, those structural walls are called as shear walls. Now here, when I have the G plus 9 or suppose G plus 10, then suppose these 2 you can say these 4 shear walls were enough to resist the lateral force. Now if I increase the height up to suppose G plus 18 or G plus 15, 16-story building. So in that case, again you will see as the height increases, again obviously the lateral force in the structure will be increasing. Okay, lateral force in the structure will be increasing, and I'm assuming that again as we have a stronger frames along the x direction, these frames are capable of resisting the lateral force. But as we are having weaker frames in the direction of y, then in that case these walls are also not capable of resisting the force which are coming from y direction. So in that case, what we need to do, we need to provide suppose I will be providing shear walls here at the outer periphery. Now you will ask me why I am providing the shear walls at the outer periphery, why not here, and why I have provided here beside the stair room and beside the lift room. Because these shear walls are structurally very good, but these are the nightmares for an architect. Okay, because it blocks most of the area. If you see here, if it is a brick wall, you can make the opening, and you can anytime, suppose you need a opening at the even after the construction, you can do that. But when you are creating a shear wall, a concrete RCC wall, in that case it is all like it is totally impossible to create openings, and anytime you cannot remove the wall, it is not possible. Okay, and it is blocking that particular space also. So architecturally it is very hard to, like, for the architects, you cannot provide shear walls everywhere. Structurally it is good, but we need to think about the aesthetic of the building also. Okay, that's why what I have done, I have provided at the outer periphery. Maybe in most of the cases you may not be able to provide shear walls like this. I'm just giving a general example. Okay, so what I have done, I have provided shear walls at the outer periphery. Now what you will see, that the total lateral force coming from the y direction are completely, you can say, completely resisted by this 1 2 3 4 4 8 shear walls. I'll just name it. Let me just name these shear walls. 1 2 3 4 5 6 7 and 8 shear walls we have along the y direction. Along the x direction we do not have any shear wall. We are totally relying on these frames, that we know that these frames are strong enough to resist the shear wall, or you can say these are having proper stiffness to resist the lateral force coming from the x direction. Okay, now if you see here what I have said that the total lateral force will be resisted by these shear walls. Then what is the use of these columns? If I consider only the y direction force, so in that case these columns will be acting. Okay, these columns will also take some lateral force, but the amount of lateral force will be very less, or amount of resistance by these columns will be very less, as most of the resistance are provided by the shear walls itself. So these columns are meant to resist the gravity loads only. Okay, as per the like in terms of resisting the y direction force. Okay, so if I just talk about the y direction frames, in that case those columns are meant to resist the gravity loads. But in the x direction, obviously, as these columns are part of these frames, so these columns will be also taking the lateral force from the x direction. Okay, so here the shear walls are also resisting the force, lateral force, and the columns are also resisting the lateral force for the other direction. So this type of structure, these are actually you can say column shear wall interactive structure or interactive system, or you can say dual system, where both the structural elements which are meant to resist the lateral force are doing their job. Okay, are doing their job. Now if I provide a few walls in the x direction also, then these four, suppose I am providing shear walls here also, here also. So again what will happen, the x direction force will be also resisted by the shear walls along the x direction, and the columns will be only taking the gravity loads. So in that case this system we will call as structural wall system, because the lateral loads are taken by the, you can say, structural walls or shear walls only, and the columns are only taking the gravity loads. So these columns will be called as gravity column. Okay, so now let us increase the height a bit more. What will happen if I increase the height? What will happen if I increase the height? So let me just go here. Let me create a simple bay now, rather making a bigger bay here. Okay, so what I will do, I will just create simple bay now. I have created a simple bay. I'll be giving the position of columns. Here, here, and rest we will be having suppose shear walls. We are having shear wall here, we are having shear wall here, we are having shear wall here, and also here. So suppose to resist the force from the x direction and resist the force from the y direction, we have provided this shear walls. Now, what is the problem with this kind of arrangement? What is the problem with this kind of arrangement? If I draw a shear wall, actually a shear wall, what actually a shear wall? A shear wall actually acts like a, if I just draw a cantilever beam, suppose this is a cantilever beam and we are having a force P from this direction. So how we will be getting the deflection? We will be getting the deflection like, right? So if I just rotate it 90 degree, if I just rotate it 90 degree like this, and the force will be coming from this direction. So this become a shear wall actually. So a shear wall, we can call a shear wall as a vertical cantilever. We can call it as vertical cantilever. Vertical cantilever. Now there is a problem with this shear wall actually. Though we have understood how it is working as a vertical cantilever. But there is a problem with the shear wall. What is the problem with the shear wall? If I just draw, a isometric view of shear wall. Suppose this is a wall, and I will draw the same here. I need to explain two things. I will draw here also. So shear walls, as we are having very less dimension in this direction, the thickness, and as we are having higher dimension in this direction as the depth, I will just write it dB and D. So obviously along this D, the depth, it will be having higher stiffness, along the B it will be having less stiffness. So this shear wall is strong enough, this shear wall is strong enough for this kind of bending, the bending which is happening in its own plane. If I just draw a plane, this is the plane of the shear wall, x and y, this is the plane of the shear wall, x and y, right, vertically. So when the movement is happening, the bending is happening along its own plane, then it is pretty stiff, or you can say pretty strong enough to provide resistance, okay, when the force is coming from this. But when the force is coming from this direction, then how we will be getting the bending? We will be getting the bending something like this. Draw the deflected shape here. So we'll be getting the bending something like this. Now here it is going out of its plane, right? It is going in the other direction, suppose that direction. So I will just write the z direction also. So it is, the bending is happening like this, in this direction. Here the bending is happening about z axis, here the bending is happening about x axis. So this bending we call in plane bending. I think this blue color is not good enough for writing. I'll just change it. So this bending we call it as in plane bending, because the bending is happening in its own axis, own plane, sorry. And here this bending is happening out of its plane, right? It is not in its own plane, it is going out, right? So this is called out of plane bending, out of plane bending. Now shear walls are strong in plane bending. It will give you it will give you more resistance in case of in plane bending, but these are very weak in case of out of plane bending. So if I just go back to the previous drawing, this particular plan, you will see that the Fx force can be resisted by the shear wall number 1 and 2, because here the D is along this direction, along the x direction, so it will be having higher stiffness in this direction. It will be having higher resistance for this in plane bending. Okay, but if I talk about this 3 and 4, these are weak to resist the Fx force. Now again, if I talk about the Fy, these 3 and 4 are weak to resist the these 3 and 4 are strong to resist the Fy force, because the depth is along the y direction. So here in this direction we will be having the in plane bending, for which it is strong, but the shear wall number 1 and 2 will be weak enough, because in that case they will be having out of plane bending, for which it is weak, right? So if I provide this kind of shear wall arrangement in case of tall building, suppose it is a G plus 20 building, or maybe G plus 30 building, I'm just assuming. So the building goes taller, so to resist the lateral force, what we have done, we have provided shear walls at the outer periphery of the building. But if you see the efficiency of the shear walls, when the Fx force is acting, these two are of no use. When the Fy is acting, these two are of no use. So the 4 shear walls are not giving you 100% efficiency, or maybe closer to 100% efficiency together for a particular direction, right? So that's why another system came up, the structural engineers came up with another system which is called the core wall. So I will just draw the similar kind of frame, suppose like this, and at the center of the at the column, sorry, at the center of the building, I will draw a box type of thing. It is made up of 4 shear walls. You can see 1, 2, 3 and 4 shear walls we have, and these are connected to each other, so those creates a box, right? And then we will be having the beams and columns. Suppose I will be having beams like this, having beams like this, like this, and then suppose here also we will be having beams, and then we will be having the columns. We will be having the columns. So before coming to this box structure, why we have came to this box type of structure? Let us just explain one more thing before coming to this box type of structure. Here, if I go back to the previous plan here, if I just provide the shear wall arrangement like this, and if I go up to suppose G plus 30, what will happen? The Fy will get weaker. Now why the Fy will get weaker? Because if I just generally write the formulas for the cantilever effect, cantilever beam, so you will see the bending moment of the cantilever. We just write the bending moment formula is, we know WL square by 2, and the deflection formula, if I just write, is W L power 4 by 8 EI. So if I give you the comparison of the power of L, so here you will see obviously with this L, it is a vertical cantilever, so it is, I'm talking about the height, it is actually WH square by 2. So let me just correct it. It will be WH square by to h power 4 by ATI, because I am talking about the vertical cantilever. So I made it h rather writing it as L length. Okay. So if the height increases, obviously the bending moment or the resistance will be increased, right? But if you see the deflection of the structure, the power above the h we are having 4. So if the bending moment increases, the deflection of the shear wall will be increased much more than the bending moment. Right, much more than the bending moment. If we are having same cross section and we are increasing the height of the structure and we are providing the same cross section, in that case the bending moment will be increased, but the deflection will be increased much more than the bending moment. Now, how we can reduce this deflection of the shear wall? So to reduce the deflection, we have only two things here, E and I, modulus of elasticity of the material, and I is nothing but the you can say moment of inertia. Now this modulus of elasticity of the material, we have limitation to increase this particular thing. Okay, we cannot use very higher grade of concrete or very higher grade of material. So we have limitation to increase this particular thing. So the only thing we are having to that we can increase is the moment of inertia. Now, how we can increase the moment of inertia? The moment of inertia, as we know, the moment of inertia depends on the cross section of the structure, cross section of the shear wall. Right now, here in this particular structure, what we have done, suppose we have made it G plus 30, and we need more resistance about this along this y direction now. And we are thinking to provide a shear wall throughout this length, outer periphery. But as I have told you, the architect will never allow you to provide a shear wall like this, and obviously it is not proper also to provide a shear wall throughout the section, because the ventilation will be you can say there will be no ventilation in this case. In this side, it will be totally blocked by the structural walls. So the architect will never allow you to provide a wall like this. But structurally, in that case, we need a wall as a whole. So why we need a wall as a whole? Why we need a wall as a whole? If I just write, suppose we have two shear walls of same cross section, B by D, B by D. And I'm talking about the force from this direction. So if I just write the moment of inertia, so how the moment of inertia of these two will be? So if I just write I will be, for these two, it will be 2 multiplied by BD cube, BD cube by 12. So it will be 2 BD cube by 12. Right now, if I make it a wall as a whole, suppose I not like this, I should not draw like this. I'm just making a wall with this like combining these two walls. I'm making a one single wall. If I make a one single wall, what will happen? What will happen? It will be 2D. I'm just adding these two now here, and the B will be the same. So let us find out now this moment of inertia for this two, and if I find out the moment of inertia for this this particular wall as a whole, combining these two walls, how much it will be? It will be I equal to B. Now the D is 2D cube by 12. How much it will be? So it will be 8 BD cube by 12. So if you see, if I'm rather providing a single wall, two different walls, if I provide a single wall combining these two depths or two you can say lengths of the wall, in that case it will give me more moment of inertia. So if we can increase the moment of inertia, obviously we can decrease the deflection of the wall or deflection of the structure, because this moment of inertia in the denominator, so it will be reducing the deflection value, right? But as I've said, it is not possible to provide a structural wall like this throughout the section. Or suppose from here to here we cannot provide giving 2D length, because it will block the airways or block the you can say ventilation, right? So that's why what we can do, we thought of providing obviously this is also failing now. This is also failing now. So there was another you can say system that we cannot provide a 2D length. Obviously we cannot provide a 2D length, but what we can do, can we add these two things with something that can give us opening also, and that can give us a similar or almost similar resistance given by this particular, the second shear wall as a whole. So what we can do, we can join these two shear walls with a very strong beam, so that it can give you you can say make these two shear walls as almost a one particular system to provide more moment of resistance for your to your force. Okay, more moment of resistance to the force. So now this particular beam that we can provide, actually it will be like this. Let me just draw a 3D view here. Suppose don't like this color. Suppose this is a wall and another wall we have, suppose here. So two different walls. In between, what we can do, we can give a beam of higher depth, which is very strong enough to transfer or transmit the forces and to make these two shear walls as a combined or as a single structural system. So we will be having, obviously we will be having openings also, though it is a deep beam with the higher depth, but we will be having the beam depth will be something like this is the beam. So what it will do, it will give you almost closer resistance as a single as the single shear wall will be giving you. But again, this beam is very hard to construct. This beam is called actually coupling beam. This beam is called actually coupling beam. Okay, this beam is called as coupling beam. So what is the work of this beam? Rather providing a single long shear wall, you can provide two shear walls and you can add these two shear walls, or you can say you can join these two shear walls using the coupling beam. Okay, and it will give you almost similar resistance to the as one single shear wall will be giving you. As the one single shear wall is not possible to provide in case of architectural thing, or in case of in the real practice, so you can provide the coupling beam. Now the problem with the coupling beam, I will just go to my browser and I'll show you one thing. Let us see the detailing of a coupling beam. Detailing of coupling beam. So if you see here, detailing of coupling beam, if I just show you some images, this image you can see, let me just open it. You can see how cumbersome it is, or how clumsy it is to provide this kind of reinforcement, and again how hard it will be to provide to do the you can say pouring of concrete for this particular beam. This is a small beam, but just see the amount of reinforcement you need to provide to you can say give that effect, or to get that effect of you can say the effect that I have just explained now. So it is very hard to provide, or it will be very critical to provide this kind of reinforcement. It is very simple, but let me show you one more. If I just have, you can see here also an image is very small. You can see the amount of reinforcement you need to provide. These are the diagonal reinforcement you need to provide. This is the deep beam, the coupling beam. These are the shear walls, two sides. Okay, so the shear walls, if this two shear walls where I have, if these two shear walls are connected with a coupling beam and giving you higher moment of resistance, then this system is called coupled shear wall system. Coupled shear wall system. Okay, fine. Now let us come to this point, as I think I should have explained this particular thing before, so that's why I have explained it. And now I'll come back to the again the efficiency of the like we understood the how we need to provide the shear walls. Now let us come back to the efficiency of the shear walls. Here we have seen that the shear walls are not efficient if you provide like this, right? Because the shear walls are weak in out of plane bending, and it is you can say stronger in in-plane bending. But here if I provide the shear walls like this, two shear walls will be acting for each particular force, and the other two will be inactive, or other two will be of no use. So obviously the shear walls we are providing, these are not giving us the efficiency that we actually wanted from them, right? So that's why the structural engineers came up with this particular system, which is called you can see at the center of the building they have provided a box type of thing which are made up of 4 shear walls, and it will be acting as a lift core. Actually, obviously it will be acting as a lift core, and this particular thing is called as lift. This particular thing is called as core. That's why I call it lift core. So at the center of the building there will be core, and we'll be having the columns and beams connected to it. So what will happen? You all know that then a single, suppose we have a I section like this, and we have a box section like, or we have a channel section like this. If I talk about the steel sections, obviously the box sections are giving us higher efficiency in terms of, you can say, moment of inertia or in terms of resistance, right? So here also this box will be giving us higher moment of resistance than a single a shear wall at the periphery of the structure or anywhere in the structure. Okay, now how we will be providing this in a real case? Suppose this is like we'll be having the lift core like this, we'll be having the lift core like this, the other side, obviously what we need to do, people have to come out from here and they need to go there like this. So what we need to do, we need to provide them opening so that they can go. So here we will be giving the coupled beams, here we will be giving the coupling beams. Now it has become a core with coupling beam, and then we will be creating the total structure around it. So this is at the center, these are the lifts, and again this will be also acting as the lateral load resisting system for the structure, and we will be providing the beams and columns. Now what is the problem with this core? Then if you are creating this kind of core, what you will see that it is taking to resist the, when we will be going very like taller and taller, like suppose 50-story building. If you provide a core, you will see that the core of the structure is taking most of the floor area, which is meant to provide for the commercial purpose or meant to provide for the like living space or something like that. So what is the main important thing that we need? The space, right? That's why we're creating the buildings. The buildings will be if it is used for the commercial purpose, then also it will be sold or it will be used, the rent will be taken as per the area that you are giving. So as the core is taking, here you can see the core, as we go higher, the core will be taking higher amount of space in each floor. So that is also an issue. The core was working very well, but now we have issue with the floor area. Okay, now we are having issue with the floor area. So now what we have got another system which is called as core and outrigger, you can say core, outrigger and belt truss system. So let me just draw this. Suppose this is my total building. Here at the center we'll be having a smaller core, like the lift shaft and all. This we have explained, but it is smaller than the one I have explained previously. And this core, suppose we have outer columns here, okay, and this core will be connected with very strong beam with the outer frame system or outer frame. Okay, and also these columns will be also connected with a very strong beam, or you can say very strong truss. Okay, now we may not get this particular thing, the outer one, but obviously we will be getting the inner one. So very strong beam means the beam will be a floor, the depth of the beam will be similar to a floor height, or a bit less. So obviously where we will be providing this kind of beams, it is not possible to give access to the people, or it is not possible, or you can say it is not serviceable, right? Or you can say it is not at every floor you cannot provide this kind of beam, it is not possible, right? So the outer one, which are outer strong beam with higher depth, which are connecting the columns, are called belt truss. It can be a truss also. The inner one are called the outriggers. Okay, the outriggers. Now if I draw the elevation, suppose I'll be drawing the elevation of what cross section? Draw of this cross section. We draw of this cross section. Suppose cross section AA. So how I will see? Suppose it is a 50-story building. I will not draw the bottom one. It is a 50-story building, and we are having the core here. Obviously we will see the core walls here. Let me draw with different color so that it will be easy for us to understand. So this is the core, right? And then we are having the floors. I will just draw the floors. Right, these are my floors. And now here we will see this outriggers also, right? We will see the outriggers also. Now we cannot provide the outriggers at every floor, obviously, otherwise if we provide it at every floor, it will be of no use, that building will be of no use. So we need to give these outriggers at an interval. So in which floors we can provide these outriggers? We can provide these outriggers at service floors, like where we keep the machineries, or like in tall buildings, you know that we used to have service floors, like you can say there will be workstations, generators, or whatever it is. So those service floors, it can be at an interval of every 7 floor, 8 floor, 9 floor, like this. So we need to provide at the service floors only. We can provide the outriggers, because the movement of people in the service floor will be very less, right? So suppose here we can provide this kind of truss. This is what outrigger is. So it will be a total floor height. The depth of the truss or depth of the beam will be of a total floor height. Suppose I am giving here at the top. So what we have done, these outer columns, the outer frame members are connected to the core with these truss elements or with these beams again. Now if I draw the cross section of these, suppose BB, so these are called outriggers. And if this is cross section AA. Okay, now if I draw the cross section BB, everything will be my column. These two are also columns. And these columns again at every floor, if you see these columns, let me just draw properly. Suppose here, here, these are the beams with higher depth. These are the beams with higher depth which are connecting to this column. So these beams with higher depth, that means it is increasing the thickness of the beam. So we can say these beams are very strong, right? So these strong beams which are connecting the outer columns are called the belt truss. Belt truss. So it is not compulsory to have this belt truss with the outrigger, and it is also not compulsory to have the outrigger with the belt truss. You can have both, or you can have any of these two. But the thing is, this particular system, when we are providing the outriggers, in that case we can provide a lesser size of the core wall. We can reduce the core wall size. So if you see here, obviously the core wall will be kind of something like this, but we can decrease the size of the core wall and we can provide this kind of outrigger system. And what it will do, it will give you the similar kind of resistance for the lateral force. Okay, similar kind of resistance for the lateral force. So in that case, here this particular thing, it can be a concrete beam or it can be a truss, as I have explained in case of the outriggers. It can be a truss also, like this. It can be a truss also, full depth of the floor. Like this. Okay, so these are the belt truss, actually you can call it. Okay, so now here, what is the usefulness of this this particular you can say core outrigger belt truss system? Here the core area will be reduced, and these outriggers we are not providing at every floor. We are providing only on the service floor. Obviously, so service floors are not for every for commercial use or for general use, right? So every service floor we can provide this kind of outriggers to reduce the you can say size of the core wall. So in that case, what will happen? We are getting higher floor area in these areas. Right now, so what we have seen, obviously here also it will not be like this. Maybe here will be also, you will be having column. So this is one system that we have called, which is like core outrigger belt truss. Now with the you can say evolution, or with the change of the trend or change of the structural mind, what the structural engineers have seen, that if I have a building like this, even with a outrigger system, we have a core wall here, okay, have beams and columns like this. I'm just drawing roughly. Okay, I just put the columns here. Right, here, like this. Okay, and it is my core wall, suppose with outrigger also. Now what is the problem? If you see the stress distribution, see the stress distribution, it will be something like this. It will be something like this for force coming from this direction. Okay, and for the force coming from this direction, it will be something like this direction. Right, similarly in this and the other direction also. Okay, so now what is the problem? You are seeing this is the stress diagram that I have drawn. Now what is the problem? Can you tell me what is the problem? The problem is, if you see that these columns at the very outer corner of the building are having higher stresses, and when you are going inside, the stress is keep on reducing. The stresses are keep on reducing. So even in this internal columns, we are not having higher stress. The higher stress is there only in the outer columns. Internal columns are not subjected to higher stress. So if we provide, obviously, if we are providing the columns everywhere in the inside also, so what we are doing, we are using higher materials which are of no use actually, because obviously these columns are not taking the lateral force, most of the lateral force, right? So what the structural engineers came up with, came up with one system where they have done, they have reduced the number of columns inside the building. Suppose it is like this, and they have increased the number of columns at the outer periphery of the building. They have increased the number of columns at the outer periphery of the building. Okay, so why they have increased the number of columns at the outer periphery of the building, as we have seen in the stress diagram? Because the outer columns are having subjected to higher stress than the internal columns. So they have reduced the number of internal columns, suppose 3, and they have increased the number of columns at the outer periphery, and these columns are very closely spaced in terms of this. Now let us understand one thing. I am considering the Fx force only. So if I draw the elevation of this particular building, and if I talk about this frame, suppose this frame number 1, so this column and this column will be creating the frame here. So I'm just drawing here, this column and this column will be subjected to higher stress. And if I sorry, not here, in between also we are having these columns. So as we are having these internal columns also, here also we are having closely spaced columns and creating the frames. And here, as we are having outer, you can say outer, at the very outer periphery of the at the very outer periphery we are having the columns. Here what will happen? This column, and it is a frame. This column, it is a frame. This column, it is a frame. Here, in case of Ex, means the force along x direction, Fx, this column and this column are creating one. Suppose just leave this particular part. Suppose this column and this column will be resisting the force. This column and this column will be resisting the force. This column and this column will be resisting the force. Here, okay, at the outer periphery we may have this kind of columns are closely spaced. Okay, so if I just start from this particular bay, so what we will see, the frame will be kind of like this. So if the force is from this direction, F, also writing the force direction F. Now here obviously if the lateral force is coming from this direction, this particular face will be under tension, this particular face will be under compression. Here also this particular face will be under tension, this particular face will be under compression. So if I just draw the reaction forces here, how you will find the reaction forces? These are the outer peripheral column. Okay. So if you see that resistant force here, as we are having tension, so the resistant force will be going down, so 1. As we are having compression here, so will there compression, so the resistant force will be going up, F2, and the distance between these two forces, this is what we call the lever arm. Suppose this lever arm 1, and the same thing we will do now here. Tension going up, so the force will be, reaction force will be going down, so F1. Compression going down, resistant force will be going up, so F2, and the lever arm between these two forces, we are having LA2. So here we are getting this LA2 is greater than LA1. So obviously if we have lever arm larger in between two forces, so the larger the system which are having larger lever arm will be giving you higher resistance, right? So in that case, if it is giving higher resistance, so the forces in the members or the elements will be less, as it is capable of resisting the force. So in that case, what will happen? The forces in the members, the structural elements will be less. Rather here what will happen? At the lever arm is less, in that case the forces in the structural elements will be higher. But in this case, as the lever arm is larger, in that case the forces in the structural elements will be less. So what we have seen, this particular system is more efficient than the system we have given here, right? The system that we have given here. Now again we are having one problem in this particular system. What is the problem with this particular system? Here also if you see these columns, the stress distribution diagram is something like this only, though we do not have an internal column. But when we see in this particular side, in this ends, the columns at the ends are having higher stress, and when we are going inside, these columns are subjected to less stress. If I talk about the Fx force, if I talk about the Fy force, same, the very corner end columns are subjected to higher stress. In this, no, I have done wrong. Talking about now Fy force, right? So I think I have drawn only this is the diagram it will be, right? So these columns will be subjected to higher force, and the inner columns, as you go inner side, it will be subjected to less force. So all columns are not giving us the expected efficiency that we wanted. Now how they have solved the problem? And again, one more thing, as these columns are very closely spaced, it is obstructing the views also, in terms of the architectural view, or in terms of, you can say, like space to provide the windows. Like when you are having very tall building at 50-story building, 40-story building, in that case obviously the view of the building or view from the building is very worthy, so you cannot obstruct the views also. Okay, so we need to keep this in also mind. Now this particular system that we thought that is very efficient, This particular system is called, as all the columns are shifted to the outer periphery, and most of few columns are given at the inner periphery, inner side of the building. So this particular system is actually called exoskeleton system, exoskeleton structural system. Now what we are seeing that this exoskeleton system is also having some problem. This exoskeleton system is also called as perforated, you can say perforated frame system, or sorry, perforated tube, like suppose you have a tube like this, and if you make smaller holes in the tube everywhere, so it will look like this. If I just make like this, closely spaced columns and then beams, you can see it is similar to a perforated tube. And this particular thing is also called as framed tube, you can say framed tube system, also called as frame tube system. Now what we have found that this frame tube system is also not very efficient, because it is blocking the view, and as the columns are very closely spaced at the outer periphery, it is blocking the view. And this particular problem here also we are getting this particular problem, that the columns even at the outer periphery also, the columns at the inner area are not giving us the higher efficiency. So what we want the lateral forces to distribute to these columns also, right? And again, one more thing, we want to reduce the number of columns at the outer periphery, and we cannot provide the column at the inner side also, because we have got the problem here. So this problem solved, we got this resolution. Now this also has a problem. Now we need to solve this problem. So how this problem was solved, what they have done, I'm just doing drawing the elevation. Rather giving the closely spaced columns, they have reduced the number of columns in the periphery. Obviously it will be same, there will be less columns at the inner side, more columns at the outer periphery, but less than it was previously. So how they have solved it, let me just draw some floors. So how it was solved, they have drawn some trusses or cross bracings like this. Like this, to decrease the number of columns and to have I can say a proper distribution of the force. Now here with this particular you can say this particular bracing system, we were able to reduce the number of columns, but the problem with the efficiency of the inner columns are not solved. This particular system is called actually truss tube system. Truss tube system. So the issue with the efficiency of the inner columns are not solved, though we have reduced the number of columns and we have got the similar kind of resistance, but this issue was not solved. This is the issue of efficiency of the inner column. So then what they have done, they have just you can say updated this particular system only. It was something like this. So the columns are reduced, the floors, and they have increased the number of you can say bracing section. They have given the bracings. I think I am not able to draw it properly. Created bracings like. Now what is happening? You can see these trusses are connected to all these columns, okay, and the distribution of the forces are very more precise than this particular truss tube system. This particular system is called diagrid system. Okay, this particular system is called the diagrid system. So with using these two things, they have solved the issue of the previous one. But after a few years, what they thought, okay, this system is also not much efficient. So now let us again draw some one box. I'm just at the end of the session, so I will just it is the last one, this last system I'll be explaining. So how we were getting the stress distribution, we are getting something, right? And now what if we divide this box into different smaller box? What if we make box to different smaller box? Now what will happen? How we will be getting this particular diagram, stress distribution diagram will be something like this. Instead of creating one particular tube, suppose this is a tube, what if we create multiple tubes in case of tall buildings when you are creating the tall structure? So this particular thing, suppose up to a certain height we will be going with these two boxes, then with another certain height we will be going with these two boxes, again for another few more height, like for another height we are going with these three boxes, and for the rest of the height of the building we are going with these two boxes. So if we create a building like this, in that case, instead of creating one particular box, what we are doing, we are dividing this box into smaller box. So the stress distribution drawing, you can say diagram will be something. Okay, so what we can do, we can distribute the same amount of stress into smaller box, and we can increase the efficiency of the whole structural system. So this particular system is called bundled tube system. Bundled tube system. Now I will show you how this bundled tube system is actually constructed. So what I will do, I will open one software which is called SketchUp. So in this SketchUp, what I have done, I have created this box and I divided into smaller boxes. So suppose up to a certain height, I am going with these two towers. Okay, with a smaller height, so no issue. Now, after that, what I have done, I want to go more. So what I have done, I have created these two towers, suppose same height. Okay, of same height. Now, what I want to go with higher, more high. So in that case, what I have done, I am creating, first let me create this. I am going higher with this blue. No, it is only visible. I am going with it. Okay. So you can see, first we have created the green tubes, and then we have increased the height with the yellow tubes. Then we have increased the height a bit more with the blue tubes, and then suppose we'll be going the top of the structure with these tubes. Another one we left. This two tubes. Now let me just show you this thing properly. Hope you can see this. What we have done, we have started with the smaller building, smaller section of the building. Then we have increased the height with the yellow one. Then we have increased the height of the building with the blue one. After that, we have increased the total height of the building with the orange one. So this kind of structural system is called actually a tube. Obviously, there will be columns and beams, there will be walls, but as a whole, I have drawn here. If I just create the boxes, the buildings as a box, so these are particularly called as tube, bundled tube system. So if I just show you an example of a real building of this bundled tube system, so let me just open this image I have downloaded from Google. This is the Wills Tower in Chicago, United States. So here you can see we have these small two areas, then this one and the other one in the other side, then these two, and then they have reached the height with the middle one. So this kind of structures, this is the Wills Tower. It's a real building made up of this this particular structural system or concept, which is called the bundled tube system. And as I have explained, the exoskeleton system, or you can say framed tube system. So if I show you the image, I don't know you can recall these structures or not. These structures are not, you cannot see these structures anymore because these are attacked by the terrorists, and these are collapsed already, right? These are the World Trade Centers in New York, which were attacked by the terrorists, and these were collapsed. So these you can say structures, these two buildings were made up of the structural system which we call the exoskeleton structure or frame tube system. So they were having closely spaced columns at the outer periphery, or we can call it as a perforated, you can say perforated tube system also. Okay, so these two towers were the a very good example of this exoskeleton structure system or frame tube system. And if I just tell you about the you can say bundled tube system. So this is the structure, Wills Tower, Chicago, in United States. So this is the example of our bundled tube system. And if you want to know, if you want to see a structure with core wall, so most of the tall buildings are having core walls. Okay, there are a few with you can say bell truss, and you can this one also, which I have called outrigger. Okay, so this is how the evolution of the structural system from the height, as per the like in case of perforated system, what we can do, like we can use the whole floor system here. We can utilize the whole floor system. In case of this one, you can say exoskeleton system, here also we are getting very higher floor area. Obviously there will be a smaller core, but the dimension of the core will be less than the core that we are having in the only core wall system here. Okay, or in the you can say outrigger system. Okay, so that is how the total structural system evoluted from lower in terms of the height of the building, in terms of the floor area of the building. You can see here we have started from these frames. We have seen the braced frame, rigid frame. We have seen the coupled shear walls, need of coupled shear walls. So we understood how we should provide the shear walls. There are many other criteria also to provide the shear walls actually, but these are the basic fundamentals. Then we have seen if you are providing the shear walls like this at the outer periphery, what is the disadvantage. Then how we have evaluated to core wall system. Then we have found out this core wall system is taking more space. Now it is about the space. So we have came up with the outrigger and bell truss system. Then again we have seen that this outrigger is also not working properly. It is not efficient. So we have came up, like even in this kind of structure where we have outriggers, then also the inner columns are not working efficiently for resisting the lateral force. So what we have done, rather providing more column at the inner side, we have shifted all the columns to most of the columns to the outer periphery of the building. So in that case, as we do not have more column at the inner areas. So obviously the cost of the structure we have reduced, right? Because the materials, we have not constructed the columns in the side, right? So the materials have reduced. Obviously the cost also reduced. Then again we came up with this one, the truss tube system. Here we have reduced the number of columns in the outer periphery. Here also we have reduced the amount of material needed. Then we came up with the diagrid system. Like these two things are similarly used. And then now we have the bundle tube system. Nowadays there are many more which are evaluating. We have you can say we have Burj Khalifa. In Burj Khalifa also, like the Burj Dubai, there also it is kind of you can say this particular system, bundle tube system, they have followed. Then we have, now we are hoping that we will be having the Jara Tower. So in the Jara Tower also there will be a new structural system. There will be core. In the Burj Khalifa also we have the core walls. And the Burj Dubai also will be having, so not Burj Dubai, it is called Burj Khalifa. Burj Dubai is the hotel, I guess. So the Burj Khalifa also having the core wall system. So this is how we have evoluted from the very basic structural system to the very advanced structural system, and there are many more. I think it is enough for us, because we will not be dealing with the tall structural systems here in this particular course, but I have just explained the need or how it is done actually. Okay, so I hope you will find this particular session informative, and in our next lesson we will be starting the thing that we are going to learn, the ETABS. So I will touch the basic you can say interface and how we can work on ETABS from the next lecture. So the first two lectures, the introductory lectures, where in the first lecture we have explained the RCC structural system, and now in the second lecture we have explained the evolution of the structural system. Okay, so I hope it is pretty clear. If you have any doubt, you can ask in the chat box, you can comment also, and I will try to clear your doubts as per my knowledge. Okay, so thank you, and we will see you in the next lecture.